This video is all about conservation of energy, which is a very important. Conservation of energy says that the total mechanical energy of an object remains constant as long as there is no friction acting on the object. To understand this law, we need to understand what mechanical energy is. Mechanical energy is not a new type of energy. Rather, it's a category of energy. Mechanical energy is equal to the sum of kinetic and potential energies. So, that's telling me that the total amount of energy, this total mechanical energy, kinetic plus potential, is the same no matter where an object is, as long as there is no friction. If friction exists, then we change the statement to say that the total energy of an object remains constant. But when we have friction, we also have thermal energy, another type of energy. When we solve conservation of energy problems, there are 5 steps that can help you along the way. Go ahead and take a moment to pause the video and write down these 5 steps. We will follow these 5 steps in the few example problems that we'll have on this video. Starting with example number 16, which is problem number 15. A bike rider is approaching a hill at a speed of 8.5 meters per second. The combined mass of the bike and the rider is 85 kilograms. The rider coasts up the hill, so he's not pedaling, and we're assuming there's no friction. We want to know how high off the ground will the bike come to a rest. We're not asking how far the bike goes, but how high off the ground will the bike be. Let's start out with step 1, define the system and verify the absence of friction. Well, our system in this case is the bike and the rider. Those two objects together make up our system, so the energy of those two objects will be constant. It says that there is no friction, so we're good on that part. Step 2 is to choose a reference level. In other words, we're choosing the point at which the gravitational potential energy is 0. To do this, it is often helpful to draw a picture. So here is the bike rider, and I have a hard time drawing bikes, so it doesn't look much like a bike, and that's okay. This bike rider is pedaling and going up this hill. Remember, we said a reference level is commonly chosen at the lowest point the object can reach. Well, in this case, the lowest point the object can reach is the ground. So that's going to be our reference level. It is commonly helpful to either draw a dashed line for your reference level or to write a little note. Something like reference level at ground. Okay, so we're finished with 2 out of the 5 steps. Step 3, identify 2 points. One that has given information and the other where you want to find information. Well, we know that as this bike rider is approaching the hill, where I have him drawn, his speed is 8.5 seconds. That's going to be one of our points. We'll call that point A. We know that that's the only spot where we know information, but we're looking for where the bike will come to rest. That'll be some point later up here. We'll call that point B. We even know some things at point B. We know the bike's at rest. So those are our 2 points. Next, we want to know, write out a conservation of energy equation for these 2 points. So, the kinetic energy at A plus the potential energy at A is equal to the kinetic energy at B plus the potential energy at B. Now we're going to identify what we don't know and kind of expand upon this equation here. This first equation I wrote is the conservation of energy equation. You should always have something that looks like this when you're doing a conservation of energy problem. Now, I'll write out the equation for each of these types of energy. Kinetic energy is 1/2 mv squared, and this is the v at location A. Potential energy, we know there are two types, elastic potential energy and gravitational potential energy. But this problem has nothing to do with springs, so we're only dealing with gravitational potential energy. Again, at point B, I have kinetic energy, and again, only gravitational potential energy. Now, I'm going to look at what I know. I know that when the bike gets to point B, it's at rest. That means that the velocity of B is 0, so this whole term is 0. I know that at point A, my bike rider is at the reference level. That means that h is equal to 0, so this whole term equals 0. I'm left with 1/2 mva squared equals mghb. Furthermore, I notice that I have a mass in every single term. So if I divide both sides by mass, the mass cancels out. So I'm left with 1/2 va squared equals g times the height at B. The height at B is what I'm looking for, so that's va squared divided by 2g. The velocity at A, we know, is 8.5 meters per second. So I plug that in, 8.5 meters per second, and square that value, divided by 2 times 9.8 meters per second squared. Notice I don't plug in negative numbers this time. We never plug in negative numbers to these energy equations. When you plug that all into your calculator, you get 3.686 meters. That is the height to which this bike rises, which is also a logical answer. 8.5 meters per second is roughly 16 or 17 miles per hour. That's pretty fast for a bike. 3.686 meters is about 1.5 times the height of the physics classroom. That's a reasonable amount to rise with that type of speed as you're just coasting. Okay, let's try another one. This one talks about a skier. The skier is starting from rest at the top of a 45-meter hill, skis down 30 degrees into the incline, and then continues up a 40-meter hill. The heights of both hills are measured from the valley floor. It tells us we can neglect friction and the effect of the ski poles. We want to know two things. How fast is the skier moving at the bottom of the valley, and what is his speed at the top of the second hill? I'm going to start, before I even start those 5 steps, with drawing a picture. I know that this height is 45 meters measured from the floor. I know that this height is 40 meters measured from the floor. The skier starts out here, and I'm just going to draw a box for simplicity's sake. Goes down that hill and back up to the top of the 40-meter hill. Step 1 is to figure out what the heck your system is and verify that there is no friction. Well, my system in this case is just the skier, and it says you can neglect friction. So we're good to move on to step 2, which is to define a reference level. I'm going to choose my reference level to be the lowest point the skier can reach, which is the valley floor. I have a nice dotted line already drawn there, And I'm just going to make a little note that that is the reference level. Step 3 is to pick 2 points. One of those points must be something we know information about, and one of the other points must be where we're looking for information. Well, I know some stuff about his initial point. Instead of calling that A this time, I'm going to call that I for initial. A point where I'm looking for information is the bottom of the valley. I don't have any information for the bottom of that valley. I want to know how fast is he going. So those are my 2 points. So I can now write a conservation of energy equation. Ki plus Ui equals Kf plus Uf. Each K is equal to 1/2 mv squared. And again, because I have no springs, my only type of potential energy is gravitational potential energy. This will not always be the case. Now I start looking at what I already know. So it says the skier starts from rest. Starts from rest means that V initial is 0. So the whole K initial is equal to 0. I also know that my final point is at the reference level. That means H final is 0. So I get to cross that one out as well. I'm left with mgh initial equals 1/2 mv final squared. Just as in the previous example, both terms contain an m. So I can cross m out and solve for v final by multiplying both sides by 2 and then taking the square root of both sides. So that v final is equal to the square root of 2gh initial. That's the square root of 2 times 9.8 meters per second squared times 45 meters. This gives me a value of 29.789 meters per second, which is pretty darn fast, but reasonable. Okay, so that's one of the things that I was looking for. It also says, what is the skier's speed at the top of the next hill? You can treat this as a new problem altogether. We have the exact same picture. I'm going to choose the same reference level, but nothing else is the same. This time, instead of having my final point, or my second point, be the bottom of the valley, my point where I don't know information is up at the top here. You can choose either the same initial point as we had, or the bottom of the valley to be your other point of interest. I'm going to choose the same initial point as we had before. So that's my initial point, and my final point is at the top of the second hill. I start this process all over again. K initial plus U initial equals K final plus U final. 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Okay, we know that the person started from rest, so that is 0. But that's it. That's the only thing that's 0 this time. He does have an initial height that's 45 meters. At the top of the second hill, he is moving, so he has a velocity, and he is not at the reference level, so he does have a height as well. Every single term, again, contains an m. So if I divide both sides by m, I can cancel it out. Remember, it must be in every term of the numerator here. So I can cancel out those two m's with that m. So I'm left with g h initial equals 1/2 v final squared plus g h final. V final squared is what I'm looking for. To solve for that, I will first subtract GH final from both sides. Then I will multiply both sides by 2. When I multiply the left-hand side by 2, I need to remember that that distributes to both terms. Lastly, I take the square root of both sides. So I have the square root of 2. Since both terms have a g, I'm going to pull that out as well. So 2 times g times h initial, 45 meters, minus h final, 40 meters. This gives a final speed of 9.899 meters per second. Again, a reasonable answer for the speed of a skier. Hopefully you're ready to try one on your own now. Pause the video here and try this problem, which is about a rock that's on the edge of a cliff. Here are the answers to this part. Part A, if you set the reference level to be the ground, the bottom of the cliff, you should have found that it has a potential energy equal to 1.96 times 10 to the 4th joules. To get that, I simply multiplied mass times g times h, which was 100 meters. Part B says, what is its kinetic energy just before it strikes the ground? That's a conservation of energy problem. The rock is my system. There is no friction because we always ignore air resistance. And so, and I have the reference level set to the ground. So K initial plus U initial equals K final plus U final. My initial point is at the top of the cliff. My final point is just before it strikes the ground. Because this rock is dropped, its K initial is 0. Because my reference level is the ground, its U final, or gravitational potential energy final, is 0. So the initial potential energy that it had is equal to the kinetic energy it has just before it strikes the ground. So again, the answer is 1.96 times 10 to the 4th joules. In part C, I use the equation kinetic energy is 1/2 mv squared, solve for velocity, and I end up getting that this rock is traveling at a speed of 44.27 meters per second. Hopefully this has helped you understand the conservation of energy law, and we'll do some practice problems on it the next time we have class.